Zoya Popovich, and I'm at the University of Colorado Boulder, and today I'm going to tell you about my view on active components for modern microwave radio frequency front ends. This is a tutorial related to the IMS 2025 conference, which is a fantastic conference, and I hope you'll attend. The outline of the talk is relatively simple. We're going to go through an introduction and then some motivation. I'll tell you about semiconductors used in front ends and give some examples of gallium nitride and gallium arsenide ICs. And then we'll finally conclude and maybe give a little bit of an outlook of what's next. So the thing I want to start with is to tell you that the spectrum, although infinite, the electromagnetic spectrum is currently very crowded, especially in the microwave frequency range. And the reason is that everybody wants to talk on their radios. The EM spectrum is a prime resource. It belongs to everyone, but because it's too crowded, it's very regulated. And so there are many financial implications. Of course, the most obvious one to everybody is the cell phone market. And as an example of the crowdedness, in October 2014, the number of cell phones exceeded the number of people on the planet Earth. So some solutions to this spectral crowding is to use spectrally efficient modulations, and that means to encode the signals that we're transmitting and receiving in very special ways to use the spectrum optimally. And also another thing that people have been doing, just as an example, are antenna arrays. And that means that we also introduce some spatial filtering or spatial properties. In other words, we can focus on one user at a time. A special case of this is MIMO, which is multiple input, multiple output. And so there are many things that people are doing. These are kind of the most obvious ones. The issues with many of these are, first of all, it's very difficult to transmit efficiently these complicated modulated signals. And so our power consumption goes up, and that implies thermal limitations and also increased complexity. So I want to talk to you about challenges in front-end design. Every radio has a digital backend, and there's a lot going on at the digital backend. And then what I'll talk about is the analog front end. And the analog front end consists of let me just put a pointer here, consists of a transmitter and a receiver, and then something that separates the transmitter and receiver and connects them to the antenna. And that can be a circulator, for example, in which case you can operate at the same frequency in theory and protect the receiver from the transmitter leakage. You can operate at two different frequencies for the up and down link, like what is done in cell phones, and that's done with a filter, and the filter demands can be very, very high. So this is a hard problem that I'm not an expert in, and I won't talk about. And then you can also switch, like in a radar, you would switch between transmit and receive. So passive parts of a front end of an analog front end include the antenna, circulator, and a filter, and then various matching networks in the transmitter and receiver, and all kinds of interconnects, including interconnects to the digital backend. Actives include gain stages, so amplification, specifically power amplification in the transmitter, low noise amplification at the front of the receiver, and then the down and up conversion, which includes mixers, oscillators, and I also count switches as an active element. My definition is if you need a power supply and a control signal, it's active. So the question is, where do software-defined radios come in here? Ideally, people would like to just eliminate this analog front end and sample directly digitally after the antenna. And that can be done. The problem is that often it's accompanied with either a very reduced dynamic range or with with increased power consumption. And so it turns out that for most high performance current front ends, there is an analog part, and it's what I'm going to talk about here. But generally, there's some challenges. And on the transmitter side, the challenges are power, efficiency, linearity, and bandwidth, and it's very difficult to get all four of these at the same time. So there needs to be trade-offs in design. On the receiver side, it's noise sensitivity, dynamic range, and bandwidth. It's very hard to get all of these at the same time. And finally, at kind of the overarching issue is the input DC power. So for all of this, we need some kind of power. And so really where this dash line goes, so that the limit between the digital backend and the analog front end really is kind of determined by optimizing often this input power, in addition, obviously, to other parameters as well. But we can't forget the power. So semiconductors have been enablers for modern wireless communications. And I borrowed this chart, so, you know, it may not be completely accurate. I'm using it here as an illustration. And this is a comparison along multiple axes of different semiconductor technologies. So for example, this is the maximum operating temperature. We have the oscillation frequency. How high can we operate? Meaning what carrier frequencies are we going to pick? And then noise figure, breakdown field, which tells us how much power a semiconductor can give. So in red is silicon, and silicon is prevalent. You know, it's a great semiconductor. It has a stable oxide. There's all sorts of good advantages of silicon, but it does have low power, relatively poor noise performance. It can operate at low temperatures only. However, it's very easy to integrate with digital electronics, and so we can make mixed signals, and it's from that perspective very powerful because it can reduce cost, theoretically. Gallium arsenide and gallium nitride are so-called compound or semiconductors. They're called 3-5 also because of where they sit in the periodic table of elements. And they have some advantages in terms of performance. Gallium arsenide can operate at high frequencies. Actually, both can, and it's low noise. It gives medium powers, and overall, it's a good semiconductor. It's quite a mature technology. It's not terribly expensive. And then gallium nitride has emerged as the power horse. It can handle very high temperatures, extremely high breakdown fields, so that means it can give very high output power, and is reasonably good in other performance metrics as well. So what about if we're trying to do antenna arrays and we want to decide which semiconductor to use for an antenna array? The example here is from the article that you see at the bottom, and this is for a cell phone base station with 65 dBm of effective radiated power. And what this means, it's a product of the gain of the antenna and the power that you're transmitting. And so you could have a big antenna with not so much power, or the other way around, and this is a measure of the power density in the far field. So what the chart is showing is, on the left axis is the average transmit power per element in an array, and on the right axis is the array gain, so focusing property. And on the horizontal axis is the number of elements. And what you see here is that if you want to use silicon, this is for SiGe, but CMOS would have a similar argument. If you want to use silicon, the output power per element is really low, and you would use many, many elements, so the antenna size would be big, and so your antenna gain would be high, and that would give you a high effective radiated power because it's the product of the two. On the other hand, if you use gallium nitride, you don't need too many elements, so your antenna gain is not very high, but your complexity is probably lower because you need very few elements. It takes a lot of complexity to connect thousands of antenna elements and their thermal implications and so on. So, and this is for 28 gigahertz with half wavelength spacing of the elements and 90% efficiency, so of the antenna itself. So, you know, some reasonable assumptions. It shows you here that maybe gallium arsenide is not a bad choice, because it gives you a reasonable number of elements where you still have antenna gain, which is nice because you have more focusing, but it doesn't have the complexity that silicon would have. So there are many trade-offs here. One that we can't really forget is the power consumption. And so this is a complicated chart. I'm not going to go into detail in it, but it shows basically that in terms of power consumption, the silicon germanium is really not that great because it simply has a lot of elements and they cannot be that efficient. And so the lowest power consumption is with about 100 elements, and it kind of is a trade-off with complexity. But really, maybe in my opinion, actually, the combination of silicon germanium and CMOS for the beam forming and all the processing, and then the high efficiency and low noise figure can be done in a different semiconductor that gives you really the high performance at the very front end. And for that, we would need some kind of integration and thermal management. So those are some of the challenges in front-end design. And I've already had this chart before, and I want to focus now on the transmitter. And so what are the transmitter challenges? Well, in a transmitter, if you make the transistor of the power amplifier very efficient, it will only be efficient at high input powers. But a communication signal varies a lot, the envelope. This is the amplitude part of the signal, and the carrier is the black in here. So the carrier may be like 2 gigahertz, and then this change in amplitude is at the modulation bandwidth, which may be, 20 to 100 megahertz currently. For LTE, it's about 20 megahertz. So you can see that for these high peaking values, the efficiency is very high. That'll be the point here. And then when you have low amplitude values, the efficiency really drops. And so what about the average efficiency? Well, there you have to consider how often the high peaks and the low peaks show up. And so if we look at the probability density function, which are these black bars on the curve, you see that most of the time, the transistor isn't actually amplifying very high power signals, so it's not going to be very efficient. And so our average efficiency is not going to be good. And so the target efficiency we'd like is this really green curve here. Another challenge is that when you make a transistor very efficient, it turns out it's very nonlinear, and that's bad because it's going to produce spectral content outside of our band where we're actually not allowed to operate, and we're polluting other people. And so how do we make this linear? That's another trade-off. And then finally, the load can vary, and that it's a whole other topic. When you're scanning an antenna array, the impedance presented to whatever is behind the antenna actually varies. And also if you use like a cell phone and you sit on it or put it on a table or so on, the impedance will change. And this is just some example measured data for a few cell phones. So these are the challenges of the transmitter. And then the other challenges come in the signal content. So signals, some difficult signals, for example, are these with carrier aggregation, and they can be distributed in the same band, they can be in adjacent bands, they can be close together or very far apart, and all of these are not that easy to amplify efficiently. In electronic warfare, one might use multiple, and that's in different kinds of communications, military communications, you may use multiple dynamic signals in a very, very wide bandwidth. And the limit of this would be an example of a multi-carrier broadband signal used, for example, in satellites. And there you may have, tens of thousands of signals, channels that are just stacked up in a, say, gigahertz or multi-hundred megahertz bandwidth. So these are all very difficult to amplify for different reasons. So how do we make a power amplifier efficient? If you look at a transistor power amplifier, it's actually the biggest contributor to losses in a front end. And so we define the drain efficiency, which is the output power, the RF output power over the drain supply power, which is the product of the drain voltage and the drain current. And then we also worry about how much power do I need to actually put in. And so the power added efficiency is the one that's of interest when we talk about a practical transmitter power amplifier. So how does one make this efficient? Well, where is the efficiency problem? The efficiency problem is that if you look at the waveforms in time domain at the carrier frequency, so this is not a modulated signal right now, this is just the carrier. So it may be, let's say, 2 gigahertz or 10 gigahertz or 28. Then you have the voltage waveform that's in blue and the current waveform that's in red for a classic linear class A amplifier. And the product of the voltage and current is the shaded, that's V times I, and that's the power that's dissipated, the heat that's generated in the transmitter, and that's what limits your efficiency. So what can we do to improve this efficiency? Well, we can change the way the device is biased so that you're conducting current only during a part of the cycle. This would be a class B waveform that conducts, where the current conducts half of the time. And you can see that the gray area is much reduced, so it's more efficient. And we can do even more things like, add harmonic content so that this overlap between the current and the voltage goes even more down, and so that the dissipation is even lower. And so that means reducing the conduction angle reduces this VI overlap in time, and so it improves the power consumption. And waveform shaping, which you can see in the last waveform, here we're adding second and third harmonic and to reduce the power consumption, but that unfortunately makes the amplifier nonlinear. And so if we go back to the power added efficiency curve, you can see that the traditional efficiency can be really good when this amplifier transistor is driven hard. But actually at this point, it's also going to be nonlinear. And so that's the trade-off we have to deal with in design. So there are a number of different power amplifier efficiency enhancement techniques. And the first thing I want to illustrate, and I'll show you examples in gallium nitride, but I want to show you why we liked gallium nitride. This is a picture of a gallium arsenide MMIC designed at Qorvo, and it's designed to put out, let's say, 10 watts. It's a huge device, and it's large in terms of area. The same amount of power at the same frequency can be obtained from a much smaller gallium nitride MMIC because the power density is a lot higher per device. And so that's a big motivation. So there are efficiency enhancement techniques that can also deal with linearity, and the most common one is a Doherty power amplifier. In a Doherty power amplifier, there's a peaking and a carrier, so there are two amplifiers basically that are combined very specially at the output. They can be digitally driven or with analog drive. And what basically happens is that the high peaking amplitudes are so for some up to some average value of the input signal amplitude, the carrier frequency, the carrier amplifier is what amplifies the signal, so this little one. And then when the signal peaks, the bigger one takes over, and this is done in a way that maintains both of these as efficient as possible. No, the bottom shows just a chip in gallium nitride at 10 gigahertz that we've made. So you can integrate this on chips, or you can make them hybrid. And these dominate in base stations and in many other systems. It's a very simple architecture. A lot is known about it. It has limitations such as bandwidth. There's been quite a bit of work in outphasing. I won't discuss those. They also use two amplifiers, work a little differently. And then envelope tracking or supply modulation is when you add a digital baseband pre-processing to the signal in a way that you actually change dynamically the power supply to the system. And I'll talk a little bit more about that. But what you can notice here that for all of these, we need a second power amplifier. And so the question is the added complexity worth it? And that's what everybody has to answer. We're adding another amplifier and all kinds of other things around it, combiners, different drive, and so on. So maybe it's just better to back off the amplifier and figure out how to manage the heat. I'll talk about the supply modulation because I think that's a very interesting approach. It's used in quite a few systems, not as much as the Doherty. But the reason I think it's interesting is that because it is carrier agnostic, it means that you can apply it at pretty much any frequency you want, and you could swap maybe the power amplifier and maintain the other part of the system. And also because it does a very nice job at managing the heat. So what do we need for a power amplifier that operates in this manner? We need an efficient PA that operates over a range of supply voltages, an efficient modulator, and all kinds of other, interconnects and so on. So it's a complicated system. And what does it do? This is an example of a measurement. So what it does is the curve that I showed you before for the power added efficiency that peaks at high values is the red curve, and that may be for like a 20 volt or 28 volt supply. But when we change the supply voltage to this RF power amplifier to lower, as we go lower, this peak in efficiency actually shifts. And so you can see that at lower envelope values, so amplitude values where most of the signal will be sitting over time, we've managed to increase the efficiency a lot. And so the average efficiency will be a lot better, and therefore the heat dissipation will be a lot smaller. That's all provided that we can make this dynamic supply. This needs to all be happening at the signal bandwidth, so we have to make the dynamic supply very efficient. The other thing is that the design of this power amplifier is not standard. You have to design it over a varying drain supply voltage. So here's an example of a 10 gigahertz MMIC that has an output power. The peak power was about 13 watts, saturated gain over 20 dB. The efficiency is close to 60%. This is continuous wave, so in pulsed, it's almost 10 percentage points higher, because you let it cool between pulses in case you want to do a radar, for example. This is done in the Corvo GaN15 process with the monolithics nonlinear model. And you can see that if we change the supply voltage between 20 and 10 volts, we can maintain the peak in efficiency. But the gain varies a lot. And this is actually an extreme example. The Corvo process is now doing a lot better. It doesn't vary as much, but it's a good illustration. And it shows you that if we want to, we would track this peak in efficiency to get the best efficiency, but actually we may want to track it differently and maintain a gain. And that's what I would choose to do, because actually the efficiency isn't bad either in that way. So the supply part of this, the dynamic supply, it needs to be very fast. So we've actually integrated it in the same gallium nitride process as the amplifier. It's very efficient. And what this particular one, we have several versions of this, what this particular one does is switches dynamically between 8 voltage levels by commutating 3 different supplies. So it approximates the envelope. This comes with some distortion that needs to be fixed digitally at the input. So what can you get from this? Well, I'm going to talk about a broadband signal. So there's 2 kinds of bandwidths. There's the RF bandwidth, which is the carrier bandwidth. So that, say, maybe would be 2 to 18 gigahertz is a very broad bandwidth, right? 2 to 4 is quite broadband. It's an octave. And then there's the signal bandwidth or instantaneous bandwidth, and that's shown here. The signal bandwidth is for an example of a 100 megahertz, 30,000 carrier satellite signal. And we have 40.8% power added efficiency on average with this amount of average power when we track. This is investigates different types of 8-level tracking with different slew rates. That's a detail. What I want to point out here is that the blue curve is if you keep the supply constant, and then the efficiency just jumps up when you do something with the supply. And you can do different things and have trade-offs with linearity, which is shown at the bottom. So you actually sacrifice linearity. It's very bad. This is a very nonlinear mode of operation, but you can do things to it. For example, you can decide to control the gate. And we have shown this is a kind of, so people do analog linearization, and but more dominant today is digital pre-distortion. That's digital linearization. I'm a believer that you should maybe try to do both, do something at the front end so that you help the digital back end. And so what we did is control, for example, the gate voltage, because what that does is controls that huge gain variation. And indeed, we were able to show that we can not only improve efficiency, but also improve linearity by doing this kind of analog linearization. So we can also have broadband signals, and I'm not going to detail this, but you can have a very broadband power amplifier, 2 to 4 gigahertz, and you're seeing here very good efficiency, about 50% over this range. And this was designed to support multiple very dynamic signals over a large bandwidth. And the approach you can take here, so this is tricky. When you have signals that are very far apart, the aggregate bandwidth is actually the spacing between the 2 farthest signals, so it can be extremely high. And what you can do in that case is actually first not add the signals, but actually add their envelopes and then track that slow varying envelope and still remain very efficient. So that's a trick. And we use that trick on an 800 megahertz bandwidth instantaneous signal, which was really two 10 megahertz signals very far apart. And we were able to show a very good improvement in average efficiency this is also at a low frequency. So, and then we looked at linearity, and indeed you can maintain this linear with some DPD and track the signal. So these are details. You can find them in the papers that are in the slides, and I'm happy to provide the slides. So the trend now is to go to higher frequencies. K-band is used for satellites, and you need to cover a very big bandwidth. This is an example of a similar circuit that was made for satellite communications, and you can see the efficiencies on the order of 40%. This is continuous wave, and the multiple curves just show different chips on the same run. And you can go higher in frequency with gallium nitride. This is done in the HRLT3 process, and it is a full transmit receive chip. It has a switch in it, and you can get 1 watt out after the switch with the 5 to 8 dB noise figure across the 75 to 110 gigahertz frequency range, which is really, really good. It includes the loss of the switch. So there's some incredibly powerful semiconductors are there. Going back to dealing with a crowded spectrum, this shows the block diagram of an antenna array where you can have different kinds of isolations between the antenna elements. The emerging approaches now are to try to use the same carrier frequency for transmit and receive. This is referred to as star or in-band full duplex. And this is a very difficult problem. And then also to use a broadband front end so you can change carrier frequencies and coexist in the spectrum. And the challenges are isolation. That's between yourself and your transmitter and your receiver. That's called self-interference when you're simultaneously transmitting and receiving. And external, when you're broadband, a lot of other signals can come in, whether they're jammers on purpose or just interference. So dealing with that is hard. This is an example of a semiconductor chip that's made in gallium arsenide, and it's an active circulator, so it avoids magnetics, which normal circulators have. The interesting thing about that is that if you have, and you can make these with high isolation, but then when your antenna load varies, which is going to happen in an array, the isolation also is not good. And this is true also for magnetic circulators. And so that's a remaining problem that would be very useful to be solved. If we're operating over a broad bandwidth, the analog the analog thing you can do at the front end is to help the digital back end cancellation, interference cancellation, and that's for this external, other signals that are popping into your band. And what you do there is, for example, you can make an active notch. So basically an active filter that also has some gain, and you can notch out the frequency that is interfering. So I just showed you some interesting kind of new avenues. In conclusion, the demands on front ends keep increasing. So it makes our jobs more difficult. We need to save power, reduce cost, improve performance, shrink the size, and so new engineering ideas and technologies are needed. And I invite you to join us and learn more at IMS 2025. It will be a very exciting conference. Thank you very much for your attention. And with that, I'd like to say goodbye and hope to see you at the conference.